So the first chapter that we're going to look at this semester is in Chapter 12 of Physics of Everyday Phenomena, and the title of the chapter is Electrostatics, right? So what is electrostatics, right? So electrostatics, and we have two words here, electro, which might give the hint of electricity, and static. Right? So we have a hint of electricity, and static means still, right? So things that aren't moving. So this chapter is all about what happens with charges that are not moving. And so what do I mean by the word charge? Right? What does it mean to say that something is charged? So the whole idea of charge is that we have two types of charge. There could be more in the universe, we just haven't found them, but for now we'll say that there are two types of charge, and we call them positive and negative. And what we have fundamentally found is that like charges repel. If I have two objects that have like charges, then like charges repel, and opposite charges attract. And this should be no surprise. As the old saying goes, opposites attract. And so, here's what we have. And I'm not going to go into the history of how we've discovered all of these things. Your book gives a pretty good historical description of what's going on. But the whole point is we have these positive and negative things, and they were found to put forces on each other. And if you recall, a force can be thought of just as a simple push or pull, right? So if we have two charged objects, then they simply either put a push on one another or a pull on one another. And this was found through various experiments by Benjamin Franklin, Coulomb, Faraday, and so on, and the list goes on and on. So what we want to talk about is what is charge? What is charge? And is there a fundamental unit of charge? Like, what is the smallest unit of charge we can have? So, to answer the question, what is charge, we have to talk about things that make up an atom. An atom is made up of charges. Right? It's made up of charges. And in the atom, we have let's just talk about a simple hydrogen atom. Hydrogen is the simplest atom. And in the nucleus, we have one positive charge, and it's orbited on the outside by a negative charge, right? So we call the positive charge in the middle, we call that a proton, and we call the negative charge an electron. All right, so the positive charge is a proton, the negative charge is the electron, and the proton carries a positive charge, as we already said, it's the positive, and the electron is the negative. Right? So we have the positive proton in the center and the negative electron in the orbit around. And these are the two fundamental units of charge. And the proton and the electron have the same amount of charge on them. So the proton and the electron have equal amounts but they have opposite signs. Opposite signs. All right, so one is positive and one is negative. And so when we're talking about charged objects, we're talking about either a proton or an electron or something that has more protons or more electrons on it. So if I have a metal sphere, for instance, there are ways in your book talks about them. A normal metal sphere will be neutral. All right, a normal metal sphere will be neutral. It will have just as many positive charges as it does negative charges roaming around. And when that happens, we call the object neutral, But there are ways that I can charge my object by either placing charge onto the sphere or taking charge off of a certain type of charge off of the sphere, leaving a net charge of the other type. So if for somehow I remove some electrons, I might have a few more protons than I do electrons roaming around. And if that's the case, we now say that this is a positively charged object. And the same would go if I had pulled more protons off of it and left more electrons on, or I could dump electrons on to the surface of the sphere. So you can have a charged object, and all of the charge is in incremental amounts of the charge of a proton and an electron. So what are the charges of a proton and an electron? So the proton and the electron, I'll just use capital P for proton and capital E for electron for right now. And these have charges of, we measure charge in units of coulombs, all right? So the fundamental unit, if you will, is called the Coulomb, after the man named Coulomb's law, which we will talk about here in just a minute. But the proton and the electron have charges of approximately 1.6 times 10 to the negative 19 coulombs. In other words, another way to think about this is to say that I need 1.6 times 10 to the 19 protons to achieve 1 coulomb of charge. So 1 coulomb of charge is an enormous amount of small individual protons or electrons. All right. So again, both of them share this number of charges, or this number of charge, pardon me, but one of them is positive and the other is negative. Now you may be wondering, what are the sizes of the proton and the electron? Well, it turns out the proton is about 2,000 times larger than the electron. This would be something like comparing the size of a tennis ball to the size of a sedan or a pickup truck. Right? So the proton is absolutely much larger in size than the electron, but they both carry the exact same amount of charge, just one of them is positive and one of them is negative. All right? Okay, so to kind of cut through all of the fluff and talk about Coulomb's law now, we need to know how these charges put those pushes and pulls on each other. Right? We want to know how they put these pushes and pulls on each other. So through the investigations that Coulomb made, he determined that the forces that these charges put on each other is proportional. The force they put on each other, two charged objects, when I mean they, I mean two charged objects, put on each other is, and we have a couple conditions here, and number one, proportional to the amount of charge on both objects, and two, the square of the distance between them. Now, this is a very intriguing result because this very closely resembles Newton's law of gravitation, or Newton's theory of gravity. And both of these laws are what we call inverse square laws, right? And it has to do with the square of the distance between them. So just to set up a quick example here, let's say that I have two charged objects. I really don't care exactly how many protons there are. We'll define how many there are in a minute. But for now, let's just say I have two charged objects, and let's make both of them positively charged. All right. So I have two charged objects, and they're positively charged, and we denote the amount of charge on an object with the letter Q. So I'll call this object Q1, and I'll call this object Q2. All right. And so the distance between them is this distance R, and knowing this information, I can write Coulomb's law now, and it's written like this. The force between these two charged objects is equal to a constant K, which I'll define here in just a minute, times the product of Q1, the amount of charge on object 1, times the amount of charge on Q2, divided by R squared. All right, so this is Coulomb's law, one of the most important equations in physics that has ever been written. So now let's actually do a specific example here and actually plug in some numbers. So first of all, let's define what this constant K is. This is called Coulomb's constant. All right, this is called Coulomb's constant here. So let me erase that. Coulomb's constant. All right, and it has the value of 9 times 10 to the 9th newtons times meters squared per coulombs squared. All right, and so remember, R being a unit of distance is going to be measured in meters, and Q's are going to be measured in units of coulombs. Right? And force must have units of newtons. So when I do my unit analysis, and we'll show that here in just a minute, all of these units cancel out, and both sides have units of newtons. All right. So let's do a specific example. Let's say that these are just two protons. All right. So now we'll set it up where I have two protons. And that being the case, right, Q1 is going to equal 1.6 times 10 to the negative 19 coulombs, and Q2 will equal the same thing. All right. So when I set, and let's let R, I don't know, let's let them be, let's say, 1 millimeter apart or so. All right, so if I have 1 millimeter, then that is equal to 0.001 meters. All right, so now let's set up Coulomb's law. So the force between these F is going to be equal to 9 times 10 to the 9th newtons times meters squared divided by coulombs squared times 1.6 times 10 to the negative 19 coulombs. And I can actually square this value because Q1 and Q2 are the exact same thing. So if I take Q1 times Q2, if they're the same thing, then this is just the same thing as Q squared. All right. When they're the exact same thing, it's just the same thing as Q squared. And so I plug that in, and then I need to divide by the square of the distance here. So I will take 0.001 meters quantity squared, And now I just need to plug this into my calculator. All right, and notice now I'm going to be working with my units. My force must have units of newtons, right? Because that's what we measure force in the SI system. And my meters squared here is going to cancel with my meters squared. Whatever I do to my number here, I must also do to my units. So if I square this number, then I must also square my units. And so I have meters squared up top and meters squared on bottom. Those cancel out. Over here, I'll also have coulombs squared. Those will cancel out. And those will cancel out with those units, and I'm left with newtons on both sides. Right? And so now when I just plug this into my calculator, you can do it in a graphing calculator, a scientific notation calculator, you can plug it into your computer, Excel will do it for you, whatever you do. All right, and you'll come up with the answer of approximately 2.3 times 10 to the negative 22 newtons. All right, not a very big force, but think of it this way, all right? Because charges are very, very, very tiny, 1 millimeter is a very large distance for two charges to actually be separated, two individual protons to be actually separated. So they're not really going to feel each other's presence at such a large distance, all right? You have to get on the distances of atomic scales for the forces to be really, really, really large. But this is just an example of actually how to carry out the calculation given two values of your charges. Now you can have larger objects that have much more charge on them, or you can have objects that are much closer. You can really figure out situations however you want or need to. But this is just a simple introduction to get you comfortable with what Coulomb's law is and how it works. And in the next video, we'll talk about the electric field and potential difference and do an example or two using both of those concepts. All right, we will see you next time.